Biconditionals. All right, this was the bell work. What I was asking kids to do is just write the converse of each of these statements and determine its truth value. So if two angles have the same measure, they are congruent. Its converse is if two angles are congruent, they have the same measure. Truth value goes both ways. If two rays create a straight angle, then they are opposite rays. If two rays are opposite rays, then they create a straight angle. They go both ways. And if an angle measures 86 degrees, it's an acute angle. Well, that's true, but if an angle is an acute angle, it doesn't necessarily measure 86 degrees, and so that only goes one way. We can go with both of these two right here and say that they will become biconditionals. This one, however, will not be. Let's go ahead and start our definition. All right, so we're looking at biconditionals, and what biconditionals are conjunctions of two conditional statements. Conjunction mean this and that. Not this or that, which would be our disjunction. And conditional statements, let's remember that inverse, converse, and contrapositive are all conditional statements. They're all types of conditional statements. So we're saying that the conditional and the converse have the same truth value, meaning they're either both true or both false, and that's always hard to get kind of used to. So in this particular case, we're going to say P this way and this way. This is the difference. It's P if and only if Q, and that's what this both-way arrow means. It means this is true and that is true, and we use it P if and only if Q. And if we're going to have if and only if, and we're going to write these sentences out and these statements out, it's nice to shorten them to IFF. So P IFF, which we say P if and only if Q. So let's look at this. A polygon is a triangle, is our P. A polygon has exactly sides is our Q. Our conditional would say if a polygon is a triangle, then a polygon has exactly three sides. That's absolutely true. The converse is also true. If a polygon has exactly three sides, then the polygon is a triangle. So because both of these are true, we can put it into a conjunction. If a polygon is a triangle, then it has exactly three sides, and if a polygon has exactly three sides, then it is a triangle. Instead of saying that big mess, these two conditional statements together as a conjunction, we just turn it into a biconditional. A polygon is a triangle if and only if it has exactly three sides. Ta-da! Biconditionals. I found this on XKCD. It's just what I find to be a hilarious stick drawing site. Honk if you love formal logic. Well, it's actually if and only if you love formal logic. That's what we're working on here is formal logic. And honk if and only if you love formal logic means doesn't matter if I'm stopped at a red light and then it turns green and then I don't move. Don't honk at me unless you love logic. If and only if you love formal logic. Har, de har, har. Here we're going to break our biconditional. Array is a segment bisector if and only if it divides a segment into two congruent parts, and break it down into what it could be, its conditional and its converse. So, array is a segment bisector if and only if it divides a segment into two congruent parts. Could be written as if array is a segment bisector, then it divides a segment into two congruent parts. That's its conditional. Now let's flip it around to its converse. If array divides a segment into two congruent parts, then it is a segment bisector. So that's how we take a biconditional and break it down into its conditional and converse. Again, biconditional means that it goes both ways. It's true this way and that way. If P is true, then Q is true. If and only if, we say IFF. P is true if and only if Q is true. Now we're moving on to what makes a good definition, and I'm going to start with the most important thing. They are reversible. For our terms today, a good definition has to be reversible. We have to use our precise terms, use our geometry language, and we have to use our commonly understood terms. A lot of geometry would just be circular logic if we didn't have defined terms, things that we accept as truths. And if we're not precise, it's not going to be good. And if we can't make it reversible, if we can't make it a biconditional, then it's not a good definition. So let's take a look at this statement, break it down to its parts, and turn a decent definition into a good definition. Our conditional. If it is an octagon, then it is a polygon with 8 sides. Our converse. If a polygon has 8 sides, then it is an octagon. So our biconditional would be An octagon or a polygon is an octagon if and only if it has 8 sides. A polygon is an octagon if and only if it has 8 sides. So that's a biconditional, and that's how we take a okay definition and turn it into a biconditional and what we would consider a better definition. So that's a fine definition. Now, a linear pair is 2 supplementary angles. Is that good or is that not good? Let's decide. Let's take it down, break it down into its conditional and its converse, and then see if we can turn it into a biconditional or not. A linear pair, if it is a linear pair, then it is 2 supplementary angles. Yeah, absolutely, because a linear pair is created by 2 supplementary angles, but we run into problems when we say if it is 2 supplementary angles, then it is a linear pair, because that we can find a counterexample with 2 90-degree angles. They do not form a linear pair because supplementary angles don't need to be adjacent. How do we turn that into a better definition? We'd have to throw adjacent angles in there somewhere to turn it into a better definition. A better definition might be it is a linear pair if and only if there are 2 supplementary adjacent angles. A little bit better definition than this.